Hi, I'm Youmin from Tsinghua University. Today, I will introduce our work Plor, a concurrent control protocol to support general transactions with predictable and low tail latency. This is a joint work in collaboration with Xiangyao, Paris, Andrea, and Remzi from the University of Wisconsin-Madison, and my advisor Jiwu from Tsinghua University. Modern data centers typically feature a high fan-out paradigm, where a client request need to be processed by up to hundreds to thousands of servers before sending a response back, where the response latency is determined by the slowest server. So the key to reduce the response time is to optimize the tail latency of each individual server. In recent years, tail latencies are optimized from different OS layers, including queue management, call scheduling, cache management, and etc. However, we find that most existing work ignore that request conflicts also have high impact on tail latencies. In modern high-contention transactional workloads, conflicts are very common. For example, as a Twitter, 25% of cluster process workloads that are highly skewed. We notice that many recent work, such as transactional chopping, are designed to optimize high-contention transactional workloads, but they mainly focus on throughput and do not consider tail latencies. Let's first use a simple experiment to show the impact of request conflicts on tail latencies. We use Silo, a classic OCC-based concurrent control protocol, to run the SSB workload, and we change the contention level. As shown in the figure, the x-axis is the throughput and the y-axis is the 99.9% latency. The latency of a transaction is measured by using the commit time minus the start time. We can observe from the figure that as the contention level decreases, the tail latency of Silo reduces by 51 times. Furthermore, we also notice that two classic concurrent control protocols, OCC and two-phase locking, perform differently in throughput and tail latency and high contention workloads. Here we will choose Silo and wind weight for evaluation. As shown in the figure, we still use the YSSB high contention workloads, and we increase the number of worker threads to measure both throughput and tail latency. In terms of the throughput, we can observe that Silo achieves a peak throughput of 1.1 billion transactions per second, which is almost 40% higher than that of wind weight. However, we also notice that wind weight delivers significantly lower tail latency than Silo. For example, for a target throughput running at 0.8 million transactions per second, wind weight's 99.9% latency is one order of magnitude lower. So our design goal is, can we think of a proper combination of OCC and 2PL in one concurrent control protocol to deliver both high throughput and low tail latency? Our answer is yes, with a novel hybridization of OCC and 2PL, which is known as pessimistic locking and optimistic reading, or Plor. For pessimistic locking, Plor follows a standard 2PL protocol to acquire locks before accessing records, so inherit 2PL's low tail latency. In the meantime, optimistic reading allows transactions to access records directly without being blocked by lock conflicts. Therefore, transaction running with Plor and avoid unnecessary blocking overhead caused by 2PL, and so delivers high throughput. Our experimental results show that Plor delivers close or comparable throughput to that of Silo, and reduces tail latency by up to 14 times. Next, I will analyze the tail latency problem of existing in-memory database systems, which motivates our design of Plor. Before diving into the details, let's first have a quick look of the working process of 2PL and OCC. A transaction running with 2PL needs to acquire the lock before accessing the corresponding records. It enforces two basic rules. First, different transactions cannot own conflicting locks. Second, once a transaction releases the lock, it cannot acquire additional locks. OCC assumes that conflicts are rare, so it processes transactions without locking records during the read phase. Instead, the conflicts are validated before committing the transaction. Since the transaction may acquire multiple locks, 2PL need a way to avoid deadlocks, and there are a number of 2PL variants for deadlock avoidance, such as no wait, wait time, and wind wait. In this paper, we mainly focus on win wait. In win wait, a running transaction is assigned a timestamp before it starts, and log conflicts are resolved by comparing their timestamps. For example, when a running transaction T1 with a timestamp of 4 acquired a log of item X, since the current log owner is empty, T1 acquired the log successfully. Then T2 and T3 comes. Since their timestamps are higher, they are pushed into the waiting queue. Now, a transaction T4 with a timestamp of 3 comes. Since it owns a lower timestamp than the current log owner T1, so T1 is killed and T4 becomes the new log owner. After T4 releases the log when it commits, it finds the oldest transaction in the waiting queue, say T2, and make it to become the new log owner. We can notice that win wait ensures that all transactions always have a higher priority to commit. By analyzing the protocol details of 2PL, we specify a number of factors that hurt its throughput, such as read-write conflicts, write-write conflicts, locking overhead, and read contention. Let's take read-write conflicts for example. When a transaction, say T1, is holding an exclusive write lock, another read has to block until T1 releases the lock. However, this is not the case in OCC, since readers don't need to acquire locks. In the figure, T2 can ignore write locks and commit the transaction directly, where another T2 fails in the validation phase, so it aborts and reruns, still using similar time as that of 2PL. At the same time, we also notice that win wait delivers much lower tail latency. By analyzing the latency distribution, we observe that a transaction's latency is highly related to how many times it aborts. As shown in the figure, for transactions that commit quickly, they typically never abort, or only abort a few times. Instead, for transactions whose latency are at the tail, they abort more than 10 times. In win wait, both transactions have a higher priority to commit, and aborted transactions still use old timestamps, and thus are more likely to commit successfully in its next retry. However, Silo does not have such guarantees, and aborted transactions still share the same chance as that of newly invoked ones to commit. Next, I will introduce the design details of Plor. Our key idea is that a proper compilation of 2PL and win wait is able to achieve both high throughput and low tail latency. And we therefore introduce pessimistic locking and optimistic reading, or Plor. For pessimistic locking, just like 2PL, transactions running with Plor need to acquire locks before accessing records. When acquiring a lock, the transaction's context, such as timestamps, are kept in the lock, enabling Plor to commit transactions with a timestamp order, which is designed for low tail latency. For optimistic reading, Plor allows transactions to ignore log conflicts and access records directly without being blocked. This avoids detecting conflicts in the read phase and further improve the overall throughput. For example, in the write figure, T2 can ignore write locks and commit before T1 commits. While the idea is simple, two challenges still need to be tackled properly. The first challenge is how to safely and correctly ignore conflicts in the read phase. And the second is how to mitigate the locking overhead, since Plor needs both read and write locks. Here is how our Plor protocol works. This is the life cycle of a transaction running with Plor, which follows a conventional 2PL for locking and unlocking. The difference lies in the locking logic. As shown here, our designed lock primitive consists of 3 states, including the writer, which is the current log owner, a reader's queue, which stores all readers that are reading the item, and the waiting writer queue, which stores all writers that wait for the lock. To acquire a read lock, the transaction simply inserts an item containing its timestamp to a reader's queue. Then it checks if the writer is committing to avoid reading inconsistent data. If so, T1 pulls if the reader owns a newer timestamp. Otherwise, the writer is killed. For read and locking, the corresponding item is removed from the reader's queue. To acquire a write lock, the transaction needs to first insert an item to the waiting writer's queue, and then try to grab the lock. If the writer is empty, it modifies this variable to itself. Otherwise, the transaction needs to wait or kill the writer, depending on their timestamps. For write and locking, the transaction first removes the item from the queue, and then finds the oldest waiter and make it to become the new lock owner. Plor commits a transaction with three phases. Let's say a committing transaction T1 with the right set of items A, B, C, and the read set of items D, E, and F. The first phase is for read-write conflict detection. The committing transaction first marks itself as committing, and then find all conflicting readers related to its write set. Among these readers, if they own a higher timestamp, then the committing transaction kills them directly. Otherwise, the committing transaction waits until the readers commit. In phase 2, the transaction releases all its read locks, and in phase 3, it commits data and releases all write locks. Due to the time limits, more design details such as match-free locker, delayed write lock acquisition, and formal proof are omitted in this talk. If you are interested, please check out our paper. We implement Plor inside DBX 1000 and modify it to support both the procedure mode and interactive mode. In interactive mode, the transaction execution logic runs on a client node, and this node sends data queries to a separate data server by sending network requests. In our implementation, we use ERPC for communication between the client node. Here I will show some of the experimental results. This is our hardware platform. Our compare systems consist of three categories, including 2PL-based, such as no-weight, weight-die, and one-weight, OCC-based, including Sino and TikTok. We also compare with existing hybrid approaches, such as MOCC, which use OCC for cold items and 2PL for hot items. Both YSSB and TPCC are used for evaluation. This figure shows the result when we run YSSBA workload in stored procedure mode. The skewness parameter is set to 0.99 with a read-write ratio of 50%. We increase the number of worker threads and measure both throughput and tail latencies. We can observe from the figure that Plor achieves 25 to 42% higher peak throughput than that of 2PL, and underperforms Silo and TikTok by 9% and 19% respectively. In terms of the tail latency, Plor shows 14.5 times and 8.8 times lower 99.9% tail latencies than that of Silo and TikTok. Also, as a compromise, Plor has higher non-tail latencies. For example, median latencies than that of Silo and TikTok, which is not shown in the figure. This figure shows the results running with TPCC workload with one warehouse. We can observe overall similar trend to that of YSSBA workload. Here, Plor even achieves comparable throughput to that of Sino and TikTok. Here is the result when we run in interactive mode, where we choose the YSSBA workload. We can find that Silo shows very low peak throughput. By profiling, we find that Silo has a very high abort ratio. Furthermore, Silo can determine whether or not to abort a transaction only at the commit phase. Here, a transaction has already issued many remote accesses for data queries, leading to high abort overhead. Plor delivers almost 2 times higher peak throughput than the second best, while still keeping low tail latencies. We specify two main reasons. First, Plor does not need to block during the read phase. And second, a running transaction can be killed at any stage, so the unnecessary overhead of remote accesses can be largely avoided by aborted transactions. Here is a brief summary and conclusion. Our proposed pessimistic locking and optimistic reading, or Plor, is a novel hybridization of 2PL and OCC. It's designed for modern in-memory database systems to achieve both high throughput and low tail latency. Our evaluation shows that Plor delivers comparable or close peak throughput to that of OCC-based approaches and reduces tail latency by 1 order of magnitude. Note that not all design aspects of Plor is beneficial. For example, if we avoid detecting write-write conflicts in the read phase, Plor may suffer performance degradation when running in stored procedure mode. Last, our code is publicly available. Thanks for watching.